The big three electrical quantities are voltage, current, current, and resistance. And in this video, you'll learn what resistance is. And we'll start as we often do with an example, a situation. Each circuit has a battery and a light, and for each circuit, we've written the voltage on the battery, which is then also going to be the voltage on the light, and in both circuits, that's 12 volts, and the current going through the light, and those are different. Here in the blue circuit, light A, the current is 4 amps, and here it's 2 amps. So the question is, which light has more resistance? And it's probably pretty easy to answer by looking at this because the batteries are identical. So this light allows less current to flow through it. This light allows more. So you have to think kind of backwards. The one that allows less current is resisting more. This one has less resistance. It's letting more current go through it. 4 cars per day in our analogy. This is only 2 cars per day. This road is slower. This is muddy. This is a paved road. This is muddy. This is slower. Fewer cars get through it per day. So the one with the smaller current here has more resistance. So light B has more resistance. Well, that was easy, and you didn't have to do any real math because both batteries have the same voltage. But pretend we're starting all over again, and pretend that these are the numbers now. So start all over, even pause the video and look at this and think about it. Would you be able to tell now which light has more resistance? And the answer is still yes. Think about what math you would do. Think about how you're reasoning this. You may want to pause and think about it until you're sure. But here's the way we can reason it. In going from the blue to the red, we've made the battery voltage 10 times bigger, 12 to 120. So if the lights were the same, we would expect the current to get 10 times bigger, from 4 to 40, but it doesn't. It only goes up to 20. So again, this light doesn't have as much current through it as we would expect. So this light must have more resistance than that light. All right, so the answer again is B. In other words, if this light were the same, we would expect it to have 40 amps, but it has less, so it must be resisting the current, the voltage more than that one is. All right, what math would you do? If you look at these two circuits, think about what math you could do with these two numbers, and then do exactly the same math operation with these two numbers so that we get a number that's bigger for the red one, for light B, because this one has the bigger resistance. We've established that. That has more resistance. So we need to use these two numbers in such a way we get a bigger number here and a smaller number there. And in fact, based on the numbers and what we had before, we want a number here that's twice as big. So pause the video and think about what math you would do. Right? And what you should come up with, like add, subtract, multiply, or divide, is to divide the voltage by the current. If you do that here, you get a resistance of 3. And if you do that here, you get a resistance of 6. So it's just what we wanted, a number that's bigger over here and in fact twice as big, which is what our kind of mathematical reasoning told us. This should have a bigger resistance and indeed be twice as big. Okay, we need a symbol for resistance. I've already given it away because it's no big secret. That R stands for resistance. That is not the unit. That's not the symbol for the unit. That's the symbol for the word resistance. All right, so our definition of resistance is defined as V over I. So we have our third important quantity, and in beginning circuits, these are the big three. There are more we can talk about, but not really in the freshman physics class. So we're done learning new quantities for circuits, really. We're just going to start using the idea of resistance in this entire next chapter. All right, here's our definition again. And these are just letters on the board right now, so I want to give you a way to think about them so that you can use them in a lab, use them to answer questions, and not get confused. And look at this diagram over here. This shows a box. The box has a resistance R. That's all in black because that's an internal characteristic of the box itself. It has a resistance. We put a voltage across it. That's the way you talk about voltage, right? You connect it to a battery, say, and we put a voltage across it. If we measure voltage, we put the probe here and the probe here. We measure the voltage across it, and that creates a current through it. The voltage is a push that creates a current through it. So notice the adjectives we use, or not adjectives, sorry, the prepositions we use. R is the resistance of the device. V is the voltage we put across the device. And I is the current what? Through the device. And you can think of I as the result. We apply the voltage. The R is an internal characteristic, and the result is a current. How many coulombs per second flow through this thing? All right, so now look at the definition of resistance and predict what the unit should be in terms of previous units, right? The unit for voltage is conveniently the volt, and the unit for current is the amp. So this would be the volt per amp. But like many of these electrical quantities, it's been renamed. So we don't have to say volt per amp all the time. And it's been renamed the ohm. It's named after a German scientist from the 1800s whose last name was Ohm. And in German, they often put an H after a vowel to indicate it's long. So that tells you to pronounce it Ohm. His first name was George Ohm, although in German, I guess it's Georg. He lived in the early 1800s, and he worked with conductors and looked at the relationship between the voltage he put across them and the current through them. All right, we need a symbol for this so we don't have to write the word ohm after our numbers. And we cannot use the letter O for the symbol. The letter 0. We cannot use the letter O for the symbol because it looks like a 0. For instance, in the previous diagram, if we had a resistance of 3 ohms, we'd write that, and it doesn't look like 3 ohms, it looks like 30. So they went to the Greek alphabet and took the Greek capital O. That's called the letter omega. It's the last letter of the Greek alphabet. It's their capital long O. You can draw it like that. You can also draw it like this. Both are okay. That's the symbol for resistance. So what we would say in that first circuit, in the previous board, we'd say that the resistance was 3. That means 3 ohms. That's the scientific symbol for the ohm. It means a volt per amp. All right, take a look at this equation. It's got a fraction in it. You're going to use it to solve word problems and solve circuit problems. So we want to rearrange it so the algebra is easier to use. So what we do, scientists in general want equations that don't have fractions if they can help it. It makes the algebra go faster. So think of multiplying both sides by I and rewrite this as an equation with no fractions in it, and you get this. V equals IR. And notice there's only 2 lines here. This is not a definition of voltage, so it would be incorrect to write 3 lines and call it a definition. This is the relationship between V, I, and R for things like light bulbs and resistors and conductors, metals, for example, heaters, for example. All right, I want to show you this little trick here. If you become an engineer, you may work with electricians or technicians, people who construct circuits and test them, but don't have a lot of math background, and they may not feel comfortable doing the algebra. Even basic algebra 1 that you may think is really easy, they may not feel comfortable with. So they might have a sheet of paper with what we call the pie on it. And the pie will be arranged like this. And I know some of you have seen this kind of thing before to make algebra easier. The way you do it is, imagine you're given 2 letters and you want to find the third. You cover up the one you want to find, and it tells you what to do with the other 2. For instance, if you want to calculate voltage, if voltage is the unknown, you cover up the unknown, and it tells you to multiply I times R. If you want to calculate I, what you do is you cover up the unknown, the I, and it tells you to take V and divide it by R. All right, that's the end of the video for the freshman 9th grade physics class. What comes next is only for the AP class. Of course, you're welcome to watch it as a preview of what you might take someday if you're in 9th grade. But you can stop the video now if you're in the 9th grade physics class. You will often hear this equation referred to as Ohm's law. And is it really a law? And the answer to that is sort of. I'm inclined to say no, it's not a law. It's the definition, is the definition. Oops, I guess I mean to put that here. Is the definition of resistance. That's what I would be inclined to call it. That there exists no concept R before you measure these things and define R this way. So you can't say V equals IR as a law because R is defined from this relationship. So this in itself is not really a law. It's sort of like Hooke's law. Hooke's law is not really a law. It's an empirical relationship found by experiment that's sort of true, but not exactly right. Same thing with the rule for friction. The force of kinetic friction equals mu Fn. That's not really a law. It's an empirical relationship, and it actually has higher order terms if you want to make it more accurate. But Ohm actually did discover something, and you could call what he discovered a law. What he did was take conductors, which means metals, right? And he put different voltages across them and measured the current. He made a table of every current he got for each voltage over a very, very wide range, many orders of magnitude. Order of magnitude means times 10 times 10. So for, say, a hundredth of a volt, and a volt, 10 volts, 100 volts. So over a very, very wide range of voltages and measured currents, he found something. He graphed them, current versus voltage, and he found that this relationship was very, very close to linear for conductors. That's the law. That for conductors, this relationship is very, very close to linear, and this has a slope, right, which is fairly constant, and so resistance would be 1 over that slope. By the way, what you call that slope, you say, why didn't he just name the slope something instead of 1 over the slope? Well, that slope does have a name. It's called conductance, and it's the reciprocal of resistance. It may come up a little bit in our AP Physics course, but not very much. Resistance is more practical to use, easier for human beings to think about, talk about, and so resistance has caught on rather than conductance. So the slope of this line is conductance, and the reciprocal of the slope is what we call resistance. So that's the law. That's what he found, is for conductors, this relationship is very, very, very close to linear. Often within the range of his measurements, it was linear. But there's a caveat. This is only if you can keep the temperature constant of the conductor, because as objects get hotter, their resistance goes up, and that's a linear relationship. As the temperature goes up, the resistance goes up in a linear fashion over fairly normal temperature ranges. And again, that's not even a law. That's an empirical finding. All right, so that's if the temperature does not change. But here is why this, even in itself, is not a perfect law. As you increase the voltage on something and run more current through a conductor, it gets warmer. So it's very hard to correct for that temperature change. Perhaps you could put it in a bath and try to suck out the heat as fast as possible, the thermal energy as fast as possible. But in the late 1800s, they found ways to correct for it, and they found out that this is correct if you can keep the temperature constant. But in general, in real-world situations, if you're thinking of being an engineer, the temperature will change. You know that your keyboard, your computer gets hot, right? Things get hot. The top of a stove, electric stove, gets hot. So with temperature change built in, this is what really happens. As the current increases, the object gets warmer, the resistance goes up, and so the slope gets smaller. Further, there are certain devices that are called non-ohmic. They're not standard conductors, and they don't have a linear pattern at all. And here's one example. You've heard of LEDs, light-emitting diodes. There are also diodes that don't emit light. But they both behave generally the same, and they have this very strange relationship between current and voltage that has practical uses here when you put the voltage on the device backwards, and here when you put the voltage on the device forward. Very useful device, but not at all linear.